7.5, where we're doing integration by partial fractions, case 3. Remember, case 1, just to review, is if you have something like the integral of 1 over x minus 5, x plus 3. Something like that. Where you have linear denominators that are out like that. You can have as many as you want. Case 2 was where we had an integral. It doesn't really matter what's on top. I'll just put a 1 again. And it's where you have a linear factor, but you could have a repeated linear factor. Like I might have x minus 5 cubed times x plus 3 or something like that. Okay, now, the third case is where we have an irreducible quadratic factor. So I'll say case 3, just to show you an example of it, it might look like something like 1 over, what if I had x squared plus 5 times x plus 3? You cannot factor x squared plus 5. If it were an x squared minus 5, some people think, oh, that doesn't factor. That person is wrong. X squared minus 5 would not satisfy for an irreducible quadratic factor because it would factor to x minus the root of 5, x plus the root of 5. This is an irreducible quadratic factor because you say, ooh, could I factor it? That's a tricky question. Could you factor it? Oh, yes, you can. But if you factored it, what would the factors be? They would be non-real factors. This technically does factor into x minus the root of 5i and into x plus the root of 5i. That is how this, and then if you say, well, let's multiply it back together. Anytime you multiply conjugates, the middle term cancels. You'd have x squared minus the root of 5 times root of 5, 5i squared, minus 5i squared is plus 5. This is the factorization of this term. However, that's not in the real number system. It's a complex factor. So when we're saying an irreducible quadratic factor, it means it's irreducible in the real number system. So let me look at our first problem with you today. So I'll say case 3, number 1. Let's say I give you the integral of z plus 1 over z times the group z squared plus 4. Integrate with respect to z. Okay, here's the only difference when you have an irreducible quadratic factor as opposed to the other. If you have a quadratic denominator, your numerator, or no matter what the denominator is, the numerator is going to have to be 1 degree less. So I can say the first factor in this would be a over z. Why is it a constant? Because my denominator is z to the first. So I have no z at all in my numerator. However, I'll say plus, this second factor is z squared plus 4. So I said, well, that's a quadratic. So my numerator needs to be a linear. So I'll say, okay, bz plus c. That's just a linear function, 1 degree less than the second power in the denominator. So I can say, okay, I need to find what a, b, and c are so I can integrate this function with respect to z. I like that. Find a, b, and c to integrate with respect to z. So now I can say, okay, z plus 1 over z times z squared plus 4 equals a over z plus bz plus c over z squared plus 4. Once again, all you're doing is multiplying by the least common denominator, which is both of these terms. Your left-hand side becomes z plus 1. Your right-hand side, when you multiply by the least common denominator, in this first term, you know the z is going to cancel. And you'll have a times the group z squared plus 4. Plus the bz plus c it's being divided by the group z squared plus 4. That would cancel with this term you're multiplying by. But then you would also have bz plus c times this z. Okay. So if I wanted to simplify this out, and I do, I could get rid of both b and c if I let z equal 0. So that's what I'll do. I'll say, well, let z equal 0. And I'll have 0 plus 1 is 1 is equal to a times 0 squared plus 4. That'd be a times 4. So 4a is equal to 1, which is going to enable us to see a is equal to 1/4. Now, once I know what a is, that is extremely helpful to find the other variables. I have a variable b and a variable c that I need to be thinking about. Okay. I know that a is going to be a coefficient of z squared on the right-hand side. What's my coefficient of z squared on the left? 0 z squared. So I'm going to be able to say 0 is equal to, what's the coefficients of z squared on the right? Well, I know a is a coefficient of z squared. Can you see that b would also be a coefficient of z squared? You could multiply it out, but I don't think there's a need to. You know you're going to have bz times, that'd be bz squared. So a is a coefficient of z squared, b is a coefficient of z squared. So I know a plus b is 0, and I already know what a is. A is 1/4, so 0 equals 1/4 plus b. B is going to equal negative 1/4 when I move it to the other side. So I know what A is, I know what B is, oh, I know what C is. Here's how. So when I look at this, could A ever be the coefficient of a Z term? It's a coefficient of Z squared and a constant. Could B ever be the coefficient of just a Z? I'm saying, no, it's going to be BZ squared. C is the only number on the right-hand side that would have a Z with it. So I know C needs to be the coefficient of Z. What is the coefficient of Z? 1. Now, if you would prefer to distribute all that, that's perfectly fine. I chose not to. But you could have easily said, in order to make sense out of what I'm saying, just distribute. And that makes it more obvious. So you say, okay, the coefficients of z squared were a plus b. The coefficients of z was only c. So that by default gave me c is 1. So I know what a, b, and c are. So I'll go into my equation and say, well, all of this is going to equal the integral of a over z with respect to z, where a is 1/4. I'm going to go ahead and factor that 1/4 out front because I know it's not going to be useful inside the integral. So I'll say 1/4 the integral 1 over z. When I factor out the 1/4 out of the numerator, I'm just left with a 1. That one's going to be easy to integrate. My next one, this one's going to be more confusing, so I'm going to show it out. Plus bz plus c. So plus the integral, negative 1/4 plus c. Sorry, that's negative 1/4 z plus c, which is 1, all divided by z squared plus 4. Okay. So when I'm looking at this, I see a problem. Well, I'm thinking, here's what I'm thinking. This would be a natural log if the derivative of the denominator is in the numerator. Is that possible? Well, the derivative of the denominator is 2z. I could force negative 1/4 z to become a 2z. I could do that. But I have that plus 1 dangling in there that's causing trouble. So separate it. So my idea here is I'm going to say 1/4 integral 1 over z dz plus negative 1/4 z over z squared plus 4. And ooh, that is horrible notation. I didn't put the dz there. Oh, ooh, that bugs me. Plus 1 over z squared plus 4. So again, the first one, easily integrable. The second one, not too bad integrable. The third one is one that's going to come back up time and time and time and time and time again. Yes, I meant to say it that many times. Because we need to be extremely familiar with this one. Probably every other problem from now on in this class is going to have this version of it in there. What does it look like? Anytime you have a variable squared plus a constant. Yeah, oh, could you do a trig substitution, 2 tangent theta? Yes, you could. That would be gorgeous. Okay, is there a quicker, easier way? Yes, absolutely. If you just remember, well, John, we know that 1 over x squared plus 1 with respect to x, that's just inverse tangent of x. Okay, so it's not too big of a step to go for, and I say we can remember this very easily, and it's going to save a lot of time and effort. Yes, it is a formula in your book, but I say it's a pretty easy formula to memorize. If you have 1 over x squared plus a squared, or a squared plus x squared, all you do is you say, well, your answer is going to be 1 over a times the inverse tangent of x over a. Let's see. That's it. So, I need to look into this problem. This second one. I'm going to use a u substitution and say, I need that denominator to be the derivative I need that numerator to be the derivative of the denominator. So I need to see a 2z up there. I'm going to force a 2z. So I'll say, okay, first term, I'm going to go ahead and just put it out of its misery and integrate it. It's 1/4 natural log of z. Done. The next one, I'll say, let's bring that minus 1/4 out front. And then I would get z over z squared plus 4. But I'm keeping in mind, and I can do a u substitution without formally doing a u substitution. You can if you can write in u equals z squared plus 4 if you want, and dz is 2z. There's no need to do that, though. Every single solitary time I can see the derivative of the denominator and the numerator, it's going to be a natural log of the denominator. So I still don't see that right now. So I'll say I need a 2z up there. So I'll multiply by 2 and multiply the outside by 1/2. Now I'm ready to integrate the last term as well. I'll keep it as it is for now. Now, let's go through and integrate. Our first term already done, 1/4 natural log of z. Minus 1/8. All of this, every single solitary time you see the derivative of the denominator and the numerator, it's the natural log of the denominator. So 1/8 natural log of z squared plus 4. No absolute values really needed there, but they never hurt. And then my last term, I recognize as an inverse tangent function. And say, well, okay, that's going to be plus a squared is 4. So this is an inverse tangent function of z with a squared equals 4. So a is 2. So I'd say it's going to be 1/2 inverse tangent of z over a, z over 2, plus your constant of integration. Now, I'm fine with that final answer. Could you combine some of these? Of course you could. I'm just saying you don't have to. Now, alternatively, because I'm afraid some of you are thinking like me, normally I don't like to use shortcuts. These problems are long enough without using shortcuts, though. So I'm saying it's a good idea. But just in case you're saying, I don't want to cheat myself and just take your word that that's the answer, I want to do trigonometric substitution to do that. Wonderful. Let's do that. So what you would have to do is you would have to isolate that term and say, well, I need to convince myself that this final answer is the integral for that. So when we use it in the future, hey, yeah, okay, that works. What I would do in this case is to say, just like Michael had mentioned a while ago, let z equal 2 tangent theta. So dz would be the derivative of 2 tangent theta. Derivative of tangent is secant squared. This would be 2 secant squared theta d theta. And so now I know z squared plus 4. That would be 2 tangent theta squared, 4 tangent squared theta, plus 4. That's going to give me 4 times tangent squared theta plus 1, 4 secant squared theta. So I would go back in here and say, well, this is equal to the integral. dz would go in the numerator. That's 2 secant squared theta d theta. My denominator becomes 4 secant squared theta. And you can say, well, 2 over 4 reduces down to 1/2. I get 1/2 the integral of, everything cancels in there except for the d theta. 1/2 times 1 d theta. The integral of 1 with respect, I think we might have had a problem on the test like this, the integral of 1 with respect to theta, just theta. So I can say this would be 1/2 theta plus c. And I can say, where theta is what? Well, z was equal to 2 tangent theta, so z over 2 is equal to the tangent of theta. Thus, theta is equal to the inverse tangent of z over 2. And so you say, okay, so it's 1/2 inverse tangent z over 2, 1/2 inverse tangent z over 2. Yeah, I was there a long time ago. So I'm just saying, yes, you absolutely could use the trigonometric substitution, but I'm saying this is going to occur quite frequently, so it's better if you just get in the habit of saying, oh, the integral is going to be 1 over whatever the square root of this number is, inverse tangent of that over the square root of that number, every time. All right, so now, hopefully you're thinking, well, that wasn't that bad. Does it get more interesting? You bet. So the easier irreducible quadratics is when you have a binomial irreducible quadratic. Let me show you the next case. So this, sorry, I shouldn't say next case. This is still case 3. More interesting problem. If I want to integrate x squared plus 2 over x times x squared plus 5x plus 8. And I'm asking you to integrate this with respect to x. Okay, so when we go through this problem, guys, we'll say, just like before, x squared plus 2 over x times x squared plus 5x plus 8. X squared plus 5x plus 8, you can't factor that. You cannot find factors of 8 that sum to get to 5. And the fact that it's an irreducible quadratic, if you tried to solve it, your solutions would be imaginary, I promise. But now you'd say, well, okay, then we'll say that this is equal to a over x plus bx plus c over the irreducible quadratic of x squared plus 5x plus 8. Okay, so now, I know I need to find a, b, and c again. I do that by just saying multiply through by the least common denominator. When I do that, the left-hand side is going to be x squared plus 2. The right-hand side will be a times the group, x squared plus 5x plus 8. Then I'll have bx plus c times only x. Now, if I, again, let x equal 0, b and c disappear. So, letting x equal 0 enables me to solve for a. I'll get 2 is equal to 8 times a, which again gives me a is 1/4. Coincidental, a is not always 1/4. So, a is 1/4. Now, if I try to solve for b, can you see that the way to solve for b is to say a plus b is equal to 1? Do you see where I'm getting that? So I know the only coefficients of x squared on the right are ax squared and b at c will not be a coefficient of x squared. So I can say a plus b has to equal 1. So I already know a is 1/4. 1/4 plus b is 4/4. So b is 3/4. I have a, I have b, I need c. Well, I know that c is going to be a coefficient of x to the first. Do I have any other coefficients of x to the first? Not b. A, yes. 5ax plus cx, that's going to be my coefficients of x on the right, so I can say 5a plus c. That must be whatever the coefficient of x is on the left. There is no x, 0. So 5a plus c is 0. 5 times 1/4 plus c is 0. It's going to give me c is equal to a negative 5/4. A, B, and C defined. So now, I could go into my problem. This is equal to the integral of a over x. 1/4 over x. It starts off the exact same way the last one did. I'll factor that 1/4 out. 1 over x dx. That's going to be 1/4 natural log of x. The next one is harder. We'll have our plus the integral bx 3/4 x plus c minus 5/4 over x squared plus 5x plus 8. So now, I'll say, okay, the first term, easy. 1/4 natural log of x. The only thing I have in these, a common mistake I'll make is, if I go ahead and integrate part of it in the beginning, I'll forget and not put it in my final answer. So just remember to bring that down in each step. It might take several steps to worry about this one. So if you already integrate part, just remember, it's always part of your answer. And I'll say, well, how am I going to integrate this one? As the very second I see the denominator is degree 2, the numerator is degree 1, I know that a natural log is part of this solution. It has to be. So I want to get the derivative of the denominator in the numerator. That's not going to be very easy. It's not going to be too hard. But what do I know I need up there? I need to see a 2x plus 5. I have a 3/4 x minus 5/4. That's pretty ugly. Okay, I'll work it one step at a time. First thing I'm going to do is factor a 1/4 out. I'll say, so plus 1/4 the integral. And if you can do this in fewer steps, that is fantastic. 3x minus 5. Ooh, dx. Bad, John. Over x squared plus 5x plus 8. I'm still thinking. I need to see a 2x plus 5 up there. The only way I can see a 2x from a 3x now is, okay, I'm going to factor a 3 over 2 out of it. So you can say, well, if I factor a 3 over 2 out, then that's the same thing as multiplying everything in here by 2/3. So I'll multiply on the inside by 2/3, multiply the outside by 3 over 2. So I'll say, okay, 1/4 natural log of x plus 1/4. I'm going to multiply by 3 over 2 on the outside because I'm taking 3x minus 5 on the inside and multiplying it by 2/3. And I do that for the very purpose I knew I needed the coefficient of x to be 2. So this is going to give me 2x minus 10/3. Okay, almost to where I want. You say, well, okay, you needed to see a 2x plus 5 in the numerator. I don't have that. But I could say, I have a negative 10 over 3. I need a plus 5. Well, negative 10 over 3 is the same thing as a positive 5 minus what? I know 5 is the same thing as 15 over 3. If I subtracted 25 over 3 from that, I would get negative 10/3, right? So I could say, negative 10 over 3. I need a 5 there. So I can say, well, positive 5 minus 25/3 is the same thing as negative 10/3. So I go into my problem now, and I'll say, okay, 1/4 natural log of x plus, this is going to give us 3/8, the integral, 2x plus 5 over x squared plus 5x plus 8. And I'm going to go ahead and put this other term in a separate integral. I could in this step say minus 25/3 up there, but I know I'm just going to separate it anyway. So instead of showing that in yet another step, go ahead and do it here. But now I know it needs to be minus 25/3, and the integral it's a part of is still multiplied by 3/8. So I'll say, okay, it's going to be this dx plus the integral 3/8 times the integral of negative 25/3 over x squared plus 5x plus 8. Are you beginning to see why I said some of these problems take patience? Oh. Okay, now. The first one's already integrated. The second one is easily integrable now because I say the derivative of the denominator is in the numerator. Every single solitary time that happens, it's a natural log of the denominator. So I'm getting 1/4 the natural log of x plus 3/8 the natural log of x squared plus 5x plus 8 plus 3/8. Now, this next one, pretty darn tough, so I'll say, I'm going to go ahead and factor this negative 25 over 3 out in front. On the integral of 1 over, I'll need to erase part of this. X squared plus 5x plus 8 dx. So, this last integral is what I need to work with. And the way I'm going to work with it is, I'm thinking, hey, this last one, it's nothing more than an inverse tangent function. It's kind of that in disguise. You can pretty much tell yourself every time, if the degree of the numerator and denominator differ by 1, it's a logarithmic function every time. So degree of the numerator and denominator differ by logarithmic function. Logarithmic function. If they differ by 2, inverse tangent function. So I can say, in order to get the inverse tangent function, I need a variable or a group squared plus some constant squared. You can get to that by just completing the square on this. So I'll say, okay, I'm going to work with that x squared plus 5x plus 8. That's equal to x squared plus 5x plus 8. I need a perfect square trinomial. Every single time it's half of the middle term squared. It's going to be 25/4. So you'll say, okay, I need to add 25/4 on the inside. If you add 25/4 on the inside, you need to subtract 25/4 out here. The purpose of writing this as a trinomial is so that then you could say it's nothing more than the binomial x plus 5/2 quantity squared. That's equivalent to that trinomial. And then what's left over, 8 is the same thing as 32/4. 32/4 minus 25/4 gives me 7/4. So plus 7/4. So right now, this is going to equal 1/4 the natural log of the absolute value of x plus 3/8 the natural log of the absolute value of x squared plus 5x plus 8. This last group, I can do some simplifying and say, well, those 3's cancel. Minus 25/8 on the integral. This needs to be put in there. And I'll say, what's the integral of 1 over x plus 5/2 squared plus 7/4? With respect to x, I'll put it up there. Ready to write my final answer, but you need to be careful with this. This is an inverse tangent function where the variable is now a group. Is that okay? Absolutely. Everywhere there's, instead of saying the inverse tangent of x, you'll just say it's the inverse tangent of the group x plus 5/2. No problem. Now, a squared is 7/4. So a is the square root. So I can say this is where a squared is 7/4. So a is the root of 7/4. A is going to be the square root of 7/2. So in my formula, I have 1 over a inverse tangent of x over a. 1 over a is just saying take the reciprocal of a. It'll be 2 over the root of 7 out in front of the inverse tangent. So I'll say, okay, this answer is final, this answer is final, the last answer is almost final. 1/4 natural log of x plus 3/8 natural log of that trinomial x squared plus 5x plus 8. Now we'll say minus 25/8 times the integral of that term. 1 over a. 1 over a is just the reciprocal of a. 2 over the root of 7. Inverse tangent of the term squared, x plus 5/2. Divided by a. Well, divided by a, I'll say I could put a square root of 7/2 in this denominator. It'd be even better, instead of putting the square root of 7/2 in the denominator, what I'm going to do is put the square root of 7 in the denominator and multiply the numerator by 2. Oh, that would be gorgeous, because what happens if you multiply the numerator by 2? It gets rid of that 5/2 and you just got 2x plus 5. Gorgeousness. That's easy for me to erase like that. Sorry for you all. So my numerator was x plus 5 over 2. I'm dividing that by the square root of 7 over 2. But if I'm dividing by a fraction, I'm multiplying by that fraction's reciprocal, which enabled me to multiply the numerator inside of that inverse tangent by 2. And then I can say, well, that would be plus c. And even after that, technically you're not done because you have to distribute the 25 over 8 through. Which I'll leave that for you. Case 4. There's 5.
There's 5 of them.
Case 4 is where you have an irreducible quadratic factor that occurs multiple times.
Yay! This sounds great.
What we just did that occurs multiple times.
No, we just did that occurs one time.
Are you sure you can do that on 2 boards?
I feel smart just writing that.
So what could I do on a test to test you over an irreducible quadratic factor that occurs multiple times without just making it a test of endurance?
Only do one problem.
Well, the problem with that is if you get it wrong, you get a bad grade. So I give you more than one problem, but I might just say...
Let us take it home?
That's an idea. I might just say, set up the integration, but do not evaluate. So you have to know what you would do as far as expanding it out, and then you have to be able to find your A, B, C, whatever else there is in there. But then just the integration part, you can stop at. So in this problem, here's what you do with an irreducible quadratic factor that occurs multiple times. You'll say, well, a over x plus bx plus c, and you'll notice the similarity of what we did with an irreducible linear factor that occurs multiple times with this. It's the same concept. Here, I'll say bx plus c over x squared plus 1 plus dx plus e. And if you're thinking, well, how far could you... I have worked a problem like, and I am not exaggerating. I went all the way through Z in a problem that had many... It'd take forever.
That's awesome.
But yes...
That's fine, we got time.
We only have 50 minutes, guys. We don't have this next
So you put a linear factor over every power of that irreducible quadratic. So if this would have been x squared plus 1 to the 4th, you'd have had fx plus g over this cubed, hx plus I over that to the 4th.
So
You'd have kept on going.
You just go like z plus a or something like that? Or
Oh,
you start using
you
double
can
letters?
use subscripts.
Yeah.
And in fact, what a lot of books
online just so we can see.
what a lot of books do to account for that, Zach, because that's a good question. They stop using A, B, C, D, E, F, G. They just use x sub 1, x sub 2, x sub 3, x sub 4, x sub 5. Then there's no limit.
Or Greek letters or something,
Oh, yeah,
right?
that's that too. But usually subscripts. So, if I wanted to solve this out, I go through and I just say, well, clearly I'm going to multiply by the least common denominator. It's going to give me 2 is equal to a times x squared plus 1 squared plus the group bx plus c times x squared plus 1 plus the group dx plus e times x. So I can say, well, okay. And some of you concerned me on the last test because you missed problems solely because of the reason you did not square the group x squared plus 1 correctly. You said it was like x to the 4th plus 1. That's a horrible mistake. A binomial squared is always a trinomial, every single solitary time. If you need to show out the FOIL by writing it by itself, please do that. This is going to be x to the 4th plus x squared plus 2x squared plus 1. So I can say, okay. Now, the bx plus c, sorry, I need to put my plus sign in there, plus the group bx plus c times x to the 3rd plus x plus, of course, I can just go ahead and say dx squared plus ex there. That's no problem. I'm confident, I mean, you could go out another step here, but I'm confident I can already just look at this and say what the coefficients of all the powers of x are on the right. So I'm not going to show another step. And if I think, well, okay, how could I eliminate b, c, and d, e? Let x equal 0. If I let x equal 0, then I'll get 2 is equal to a times 1. I know a is 2. Now, using that information, along with the information, I could say, okay, could I get an equation for the coefficients of x to the 4th on the right-hand side? Ax to the 4th plus bx to the, that's going to be the only ones that are coefficients of x to the 4th. So I say a plus b are supposed to be coefficients of x to the 4th. Well, the coefficient of x to the 4th on the left is 0. So since a plus b is 0, that tells me b must equal -2. Have my solution for a, have my solution for b. 3 more to go. I go down to the x cubed terms. A is not a coefficient of x cubed. B is not a coefficient of x cubed. C is. So I could say C is a coefficient of x cubed. No other coefficients of x cubed. What is C equal to then? The coefficient of x cubed on the left, which is 0. We can see that C is 0. I move on to D. Sorry, I move on to the x squared, which may be, well, it is D. The x squared terms on the right. 2a is going to be a coefficient of x squared. Then I'd say b is going to be a coefficient of x squared. bx times x is bx squared, so plus b. C would not be a coefficient of x squared. D is, and I know that the coefficient of x squared on the left is 0. Now, I know A already, I know B already. That enables me to solve for D. So I'll have 2 times 2 is 4, minus 2 plus D is 0. So I'm getting 2 plus D is 0. Thus, D is -2. Final step, well, maybe the final step, I need to find out what E is. That's going down to x to the 1st. A will not be a coefficient of x to the 1st. B will not be a coefficient of x to the 1st. C would be. So I'll say C plus E are my coefficients of x, and that needs to equal 0. Well, I already knew C was equal to 0. So E is also equal to 0. And that's as far as I need to go. So I'll say, okay then. I have this problem worked out as far as the numbers A, B, C, D, and E that go in there. So this is going to equal the integral. A over x, where A is 2. I'm going to go ahead and factor that 2 out and call that 2 times the integral 1 over x dx. We know that that's 2 natural log of x. I move to the next term. bx plus c over x squared plus 1. So I can say, well, b is right here. That's going to be minus 2x plus 0. So I'll get plus the integral, negative 2x over x squared plus 1 with respect to x. I add to that plus the integral dx plus e. Here's d, negative 2x plus e over x squared plus 1 quantity squared with respect to x. So I look at this. The first term, easily integrable, 2 natural log of x. The next term, easy to integrate. The derivative of the denominator is 2x. We can manage that. It's just the negative of the derivative, so that can be brought out. Call it the natural log of the denominator. This term, that's more of a problem. We don't have simply a variable squared plus 1. We have a group squared. But when I look at that group, I do see, once again, I kind of see the derivative of that denominator in the numerator. This one's going to work out pretty nicely. I'll go ahead and attack it. I think this one's shorter than the previous problem. 2 natural log of x. In the next one, what I would recommend, instead of showing another step, I'll say this negative comes out, and I'll say minus the integral of 2x over x squared plus 1 is the derivative of the denominator and the numerator. Yes. Every time that happens, it's, and I'll bring the minus out, minus the natural log of the denominator. I move to that last term. This is the one I need to work with. So I'll say, and if you wanted to pull it aside or something, I'm fine with that. I'm going to pull it down here and say, I need to work with that negative 2x over x squared plus 1 quantity squared. Say that again, please. Sure. I can do that. I was going to go ahead and just do a u substitution on it. Sorry, not u squared. U is going to equal x squared plus 1. So du is 2x dx. So I know I can simplify this in terms of u and say, well, this is going to equal the negative of the integral. 2x dx is all du. And I get this is just going to be the negative of the integral 1 over u squared du. Which gives me the negative of the integral u to the negative 2 du. Okay, when I integrate that, this is going to become u to the negative 1 over a negative 1 plus the constant of integration. So I can say, okay, I know that this negative and this negative are going to cancel, and I'll have 1 over u plus c. That is all of this last one, where u is the group x squared plus 1. So all I need to do is go back into here and say, this last group is nothing more than plus 1 over the denominator, x squared plus 1, plus the constant integration. Are you seeing where that's coming from, guys? Is that okay? I shudder to do this. This next one, the reason I want to show it to you is because not every time are you simply going, and this might be one of those problems where I say, just set it up. Not every time can you easily be able to figure out what your variables are. So far, all of the problems I've given you, you could figure out your variables through just plugging in a value for x and then being able to solve for the other ones. It's not always going to be that easy. Sometimes you're going to, and I know in some other classes you may have been given a system equation solver. In my opinion, those are pointless. Who needs an equation solver when you can just use a matrix? It's what a matrix is for. So I'll say in this next problem, an equation solver or a matrix is going to be necessary. And I think you'll see what I mean when I show you the problem. So if you have an equation solving program on your computer, it could be useful on this one. I won't. I'll just use a matrix. So I'll say, what if I give you x over x minus 1 times the group x squared plus 2x plus 2. Quantity squared with respect to x. Okay, so I'll go through the problem and say, well, all right, I know that when I try to find my A, B, and C, I'll just go ahead and write this out. And actually, I'll go ahead and skip the step where I write all that. I know I would multiply by the least common denominator, so this is just going to give me x. Well, sorry, I'll go ahead and show that. I don't want to be confusing. It's confusing enough without me being confusing. I'll say a over the linear factor plus bx plus c over each of the irreducible quadratic factors, x squared plus 2x plus 2, and then plus dx plus e over x squared plus 2x plus 2 quantity squared. So I would say, okay, in a problem like this, I want to go ahead and simplify out. I know x is going to equal, a is going to be multiplied by this entire group squared. Plus bx plus c is going to be multiplied by x minus 1 and another one of these groups. Plus dx plus e simply just times the linear factor x minus 1. So these problems really become more of an algebraic process than it is testing your integration abilities. In this first one here, I'll say, okay, x is equal to a times the group. You could write this x squared plus 2x plus 2 times x squared plus 2x plus 2. Distribute every term of the first group to the second group. I've already done that because I didn't want us to take time doing simple algebra. And it's going to be x to the 4th plus 4x cubed plus 8x squared plus 8x plus 4. When I algebraically multiplied these three terms, I got plus b times the group x to the 4th plus x cubed minus 2x, and I got c times the group x cubed plus x squared minus 2. Then I had d times the group x squared minus x and e times the group x minus 1. Now that's just multiplying. Once I get to that part though, this one significantly harder than the other ones to try to solve for a, b, and c. I could solve for a by saying let x equal 0 and well actually that wouldn't solve for a because you'd have to let x equal 1. I apologize. If x is 1, it cancels out the b, c, d, and e terms. And for the A term, you could say, well, I could plug a 1 in, I'll get a value, and that would enable me to solve for A. That's not going to be that helpful, though, because I promise you, you're still not going to be able to go in and solve for your other variables. You have too many variables. So what I would do, I would create what we have as a matrix. You know, okay, it keeps on talking about this matrix. Same thing as I was doing before. You'll say the coefficients of x to the fourths form your first equation. So you'll say you're going to have a plus b. That's your coefficients of x to the fourth. And I know that a plus b must equal 0. First equation. Second equation. The coefficients of x cubed are also equal to 0. I know 4a plus 1b plus 1c no d or e. All of these are coefficients of x cubed. The sum of the x cubes has to be 0 since there's no x cubed term on the left. I move down to x squared. 8a, and then I don't have a bx squared, plus c plus d. All of those are coefficients of x squared. The sum of the x squared coefficients must equal 0. I move to the x coefficients. I have a 1 over here, so finally I can set it equal to a number other than 0. I know 8a is the coefficient of x, minus 2b, and then I could say there is no c coefficient of x, minus 1d, and plus e. And I know all of those variables must equal 1. So I'll say, okay, now, last one, the constants. 4a, b's not a constant, minus 2c, d is not a coefficient of a constant, minus e. All of those must sum together to be the constant on the left, which is again 0. So now what I need us to do is to be able to create a matrix in which the columns are going to represent each of the variables. I'll have an A, B, C, D, E, and then I'll have a column of solutions. So my first row of the matrix, A and B, 1 and 1, everything else 0. The second row of your matrix, 4, 1, 1, everything else 0. The next row, 8, you don't have a B term, so be careful with that. 8, 0, 1, 1. Everything else 0. Now I'll have 8, negative 2. There is no C, so 8, negative 2, 0, negative 1. Uh, 1 and then 1. And then my last row, 4, 0, negative 2. 0, negative 1. And 0. Now, the calculator already has a gorgeous feature built into it that takes all of this, solves it out for you without really any effort at all. So I'll go in here and go matrix edit. Any matrix, you have to say how many rows by how many columns. It has 1, 2, 3, 4, 5 rows. 1, 2, 3, 4, 5, 6. This is a 5 by 6 matrix.
Where'd you see edit?
Oh, I'm sorry. I just rushed to that, didn't I? So you go second matrix, and then if you arrow all the way over to the right, Clint, you should see the edit. Okay, and then you just enter in. I always use matrix A, and then you'll have to say it's a 5 enter, 6 enter matrix, and it allows you to put each individual entry in there. Now, I think I have mine entered okay. Once you do, you hit second quit. And I would recommend, just to make sure, because that's 30 terms that you could enter in wrong, I would go second matrix, A, and just hit enter. And it will display on your screen the matrix you've entered in. And if you need to arrow over to the right to see any columns, it will enable you to do that. So just to double check, this is the matrix I entered in, and it looks like, yes, I have entered mine correctly. Now, in order to see the solutions, all I have to do is row reduced echelon form. What it's going to guarantee you, if you have it in row reduced echelon form, is that your first row is going to have a 1, and everything else is zeros until a solution. So I'll say this is A, B, C, D, E, and answer. Is this going to be 1, 0, 0, 0, 0, and some answer. My second row, guaranteed some answer. I just need to find the answer. So clearly the first row is going to tell me what A is, the second row B, the third row C, and so forth. So to get to that, I just go matrix, math, arrow up is the quickest way, and I need to choose row reduced echelon form of matrix A, and it's telling me my values. So A is, now let's say you're thinking, but those decimals aren't so pretty, John. Math enter.
Can you go back to how you get to that?
Sure. As far, the row reduced echelon form? Yeah.
Sorry.
That's right. I'll zoom out a bit. So what I would do, once I have the matrix entered in, off of that screen, I quit out of that. Then I go second matrix, arrow over to math. Glare. I'm trying to get rid of the glare. Ooh, got rid of it. I arrow over to math, row reduced echelon form. Now, you have to make sure to say row reduced echelon form of matrix A. You can't just type in A. You have to say of matrix A. And it gives you that. I would probably prefer fractions. So math, enter, gives you the fractions. So you.
Well, it's probably going to sound like a stupid question. But, I know it's just some kind of program you have on your calculator.
No, this is not a program.
But how do you get your fractions to display like
Oh,
You have to have
it's
the
because
math script.
I have the update, you don't. It's
You
no
can
big
take-
deal. I can give you the update.
Yeah, it's not.
Yeah, I'm guessing it's.
When you go to put
But
fractions,
your fraction, yours should still show the fractions, just not.
it does.
just
it's
not
just
in the
not
pretty
pretty.
print.
you can put all your fractions in like actual fractions.
I want pretty fractions. Somebody give me pretty fractions. I just want the update.
Negative 1/5 and 2/5.
Mine 3/25 turned out to be something kind of goofy.
And then
Plug that
bottom
really
A, B, C, D, E.
Yeah.
Yes.
everything else is
Yes.
correct.
This is the A, this is the B, the C, the D, and the E.
Yeah, they all.
So now after doing this, you'd go back in and fill in all these values. So you'd have the integral of 1/25 over x minus 1 plus a negative 1/25 x minus 3/25 over this plus negative 1/5 x plus 2/5 over this group squared. Okay. Now, so we could do that hypothetically. Would that be the best use of the rest of our class? Probably not. I'm with you on that. But what I will do, I will say, you will have a problem in which you're forced to use an equation solver or a matrix to where you'll have to tell me what the A, B, C, D is, something like that. So you'd be able to stop at this point and not work it any further. I might have you set up the integrals, which just means setting it up and plugging into A, B, C, D, and E, which would be easy to do.
And if we finish it, we can
No. Too much extra credit.
How do you scroll through your matrix?
Oh, I just hit arrowed down and arrowed up. So like, if I need to see the top port, now once you hit enter, I don't think it'll do it anymore. But yeah, I can still arrow down and arrow up, or arrow to the left and right, should be fine. Yeah, it should work. Now, if yours isn't scrolling, go back, do the matrix row reduced echelon form of A again, and once you first enter it, it should enable you to scroll back and forth. Okay, now, case 5. And case 5, some people would do as case 1, or probably case 2. It's one of our easier cases.
Yay!
And I thought it would be wise to do after 3 and 4 to kind of be oh, okay, these aren't so bad. Case 5 is where the degree of the numerator is equal to or greater than the denominator. Looking at this problem, case 5, every single solitary time, if the degree of the numerator is greater than or equal to the denominator, you're going to go back and use the technique that you did in pre-calculus, 1710 pre-calculus, in fact, long division of polynomial functions.
Yay!
Once you do the long division, it makes it easy. Now, I went ahead and put placeholders for all the variables, and that you don't really have to do that. It's probably good to, but you don't have to. X cubed goes into x to the 4th x times. I'd go over my x term here. X times x cubed is x to the 4th. X times 9x is going to give me 9x squared.
Are those zeros?
Yes.
Just
I don't know how to do this.
I'm having a flashback for a second. You
Should. I'm subtracting that out, guys. And so I'd say x to the 4th minus x to the 4th cancels. 0x squared minus 9x squared, negative 9x squared. And then I could say, well, I could bring down the 1. I'm not going to just yet. You can. My next term, you'd be saying, how many times will x cubed divide into 9x squared, or negative 9x? It won't. So we're already done. What I can do is I can say, so this integral, x to the 4th plus 1 over x cubed plus 9x dx, Oftentimes you'll have to do your division more steps than just this. This time there was only one time. And I can say, so it's equal to the integral of x, because here I've just shown that x to the fourth plus 1 over x cubed plus 9x is equal to x, and then it would be plus a negative 9x squared over x cubed plus 9x. That was the point of the long division to get to that. So now I can integrate it and say, well, my first integral is just going to be this term with respect to x. Then I would have, you could say plus a negative 9x squared inside the integral. I'm going to go ahead and say minus 9x squared over x cubed plus 9x dx. Okay, so my first one, obviously that's just a 1/2 x squared plus c. I'll say 1/2 x squared. I'm going to leave the c for later. This next one though, I don't know. I'm going to go ahead and simplify it. I'll say minus 9x squared over this denominator factors. I could factor out a common factor of x. I would have left x squared plus 9, irreducible quadratic factor. So now I have to pull apart that second interval there and say, okay, I need to think about that term. So now it's a case 3 problem inside of a case 5 problem. I can say 9x squared, and this one will not be bad. Whenever you combine techniques, I promise you, it's not going to be bad. I'll say it's a over x plus bx plus c over x squared plus 9. So I can say, okay, so 9x squared is equal to a times the other denominator, x squared plus 9, plus bx plus c times x. So I can say, okay, if I allowed x to equal 0, that gets rid of b and c. And if x is 0, the left-hand side is 0. The right-hand side would be 9a. So we know a is 0. That helps. Because now I can take that information along with being able to see that a is a coefficient of x squared. B is also going to be a coefficient of x squared. So I know a plus b absolutely has to equal the coefficient of x squared on the left, 9. I already know a is 0, so b is 9. And then when I look at c, I can see it is going to be the only coefficient of x. A is not a coefficient of x, and the coefficient of x on the left, again, 0. So c is 0. You always want these to be 0. The more zeros you have, the more your problem is easy to integrate. So I'll say, okay, this is equal to 1/2 x squared minus the integral of, so this integral 9x squared over this simplified down, 0 over x, that's just 0, so don't have to worry about that one, plus bx plus c, plus 9x plus 0. The only thing I'm getting out of all of this is just 9x over x squared plus 9. So this is an equivalent expression to what I have there. Is it much easier to integrate? Way easier to integrate. I can say, I can automatically see it's going to be a natural log. Why? The degree of the denominator and numerator differ by 1. What do I want to see in the numerator? A 2x. I don't see a 2x. So move the 9 out. Goes out there. You need a 2 in there. Put a 2 in there. But if you multiply by 2, then you need to divide by 2 on the outside. So now I can say, okay, this is simply going to be 1/2 x squared minus 9 over 2 natural log of x squared plus 9. Plus c. You see.
That's a little confusing to keep using dx and c in the long
Yeah,
way.
yes, yeah. Good point.
I keep hearing that and thinking,
Yeah.
it's over,
He's
right?
done. No.
This might just be a complete algebra mistake, but can you not just factor an x out of the denominator and then cancel with an x in the numerator, and then you have that easy thing that we did all that stuff to get to? Or, you know,
That kind of defeat. No, you could. That just defeated the purpose of the problem I was working, because you're not always going to be able to do that. But I like that you see that you could have done that. Yeah, yeah, absolutely. So Zach asked a very intuitive question. Shock? No, just kidding. So Vernon didn't even know it. So notice up here, guys, algebraically, you could have just reduced it down by a factor of x over x. It would have led you down to this or down to what I had here before I changed it. Okay. Would have left you with 9x over x squared plus 9. But I wanted to show it using calculus, but you could show it using algebra.